Okay, this is going to be a quick tutorial for this solar-driven design using Cellular Automata tool. This is a parametric and generative design tool that you can use during the early design stages in high-rise built environments when designing for maximum solar radiation considerations. And it is a context-sensitive tool so that it's going to be informed by the context of the site of your building with regard to the solar radiation. So I'm going to give this tutorial assuming that you have either read some of the research paper or watched the research presentation. And if you haven't, I would encourage that you do so because it will give you a deeper understanding of the concepts and processes that are used in this tool. For the sake of this video, I'm just going to try to keep it brief and show you how to actually use the tool in Grasshopper and how to kind of navigate through it. So if you haven't read the research or watched the presentation, no big deal. The goal is for this to be pretty intuitive. Even if you're kind of new to Grasshopper, that's okay. But if you wanted to look at the research, you can find it at this website, urbilab.com. That's the Urban Intelligence and Integrity Lab for Southern Illinois University. So to use this tool, you need a few components. You'll need the Ladybug tool for the radiation analysis. It's a pretty well-known tool. So hopefully you've heard of that or already have that installed maybe. And then the other two are a little less known. There's Anemone, and that's for looping the workflow, which isn't normally possible with Grasshopper's default components. And then lastly, there's Rabbit, which is a component for the Cellular Automata, which I'll get to. And Anemone you can get at Food for Rhino, but Rabbit you have to go to this other website, but they're pretty easy to download and get installed onto your Grasshopper. So before I get started, I'll just kind of do a zoom out here and give a brief explanation about how I have it organized. So in these white groups, these are the actual tools, the main tool, the main process that's happening. So it's organized into two steps. You have the first step that generates the form, and you take that output and plug it into step 2, and that second step will clean up the tool or clean up the output from step 1 using Cellular Automata. And then the output from that is your final output that you can use to kind of inform your early stage designs and form finding explorations. So that's that portion. All of the inputs I have highlighted in green. So you have these main inputs, and then you also have the EPW input over here, which that's what we'll start with. And then lastly, I just have some example scenarios grouped up in yellow here. You have analysis periods here in the middle. These are at the top. These are the scenarios that we used in the research. So for each of these 3 cities, there's all of that information. And then at the bottom, these are just some example outputs that you can kind of look at. Okay, so starting with the inputs, we'll start first with the EPW file, which if you've used Ladybug before, you know that it kind of all runs and revolves around an EPW file. That's the file that contains all of the weather information. So we need to get that first. And the easiest way, I think, is to set that to true. I need to reshare. Set that to true, and it automatically opens up your browser and opens up this map of all of the EPW files that you can use. So yeah, you can just like find wherever your project is or wherever you're working at. It's just these little dots. Let me find a different one because there's different types of EPWs Usually the TMY3 are the better ones. So here, for example, you have TMY3 and then TMY3, but this one is TMY2. You're supposed to use the TMY3. I don't know exactly. That's kind of the standard one. So you click on whichever one you decide to choose. That, I mean, both of these would be kind of interchangeable. And then you copy the link to clipboard. I'll reshare again. Copy the link to clipboard, and then you just paste it into this panel here. And after you do that, you can plug it into here where it says weather URL. I'm not going to use that one. I'm going to use one of these example URLs that I have. So this one's for Minneapolis. You just plug it into there. It takes a second, but by doing that, you're just giving it all of that information specific to that location that you chose. Okay, so that's the first step. And then moving on to all of these other inputs, I'll just go top to bottom. You have the analysis period. This is so the simulation knows what period to analyze. Otherwise, it'll just analyze like an entire year, every hour of that year, and it will give you a lot of unnecessary information and take longer than it needs to. So here are some example analysis periods that I have. You have the annual one at the top, and then just broken up into seasons at the bottom. And you like feel free to make your own. If you wanted to optimize something for just a single month, you could do that. But we're just going to do the annual one for now. And you can see I only did it because this is a solar-based simulation. I only did it for hours where the sun is out. So we won't get any unnecessary or unneeded information. And all of these inputs, they're already plugged in to everything, so you don't have to mess with that too much or at all. I just hid them all, so it's like easier and more legible to understand. The grid size is, let me turn one of these on to help explain this. So this is an example of the kind of output that will be generated. It's a little hard to see, but you can see the form is made up of these little cubes, and these cubes are called voxels. It's nothing more than just like a three-dimensional pixel. And these voxels are, it's just the medium that the form is communicated in. It's just how the form is represented. And what you're defining here with this grid size is how granular you want the form to be. So this is set to 10, and that's what we use for the research, meaning that each of these voxels are 10 cubic feet. And 10 is kind of, we decided was a good balance, because it's, when you are generating a form this big, you can still get some kind of free form granularity from it. But if we were to go smaller, like 5 or 2 feet even, then you could imagine it would be creating or generating like millions of voxels, and it would get very time consuming and kind of hard on the computational system. So be careful with making this too small. I think 10 is fine, but yeah, you could play around with it. The number of voxel layers, this is just saying how tall you want it to be. So this is saying like after 50 layers, voxel layers in the Z direction, the system will terminate and end. If you don't define that, then it would just like keep going for however long. So this could like be a representation of how tall you want your eventual building to be. So yeah, 50 is fine for now. And then the target volume percentage. So I'll be able to explain this a bit better whenever I start the simulation. But this is just saying if you can imagine a wireframe box, if you can imagine a wireframe box around this voxelated form, what percentage of that box has a voxel? What percentage of that box is has volume in it? And in this example, it's 50%. That's just to have something to optimize for, because it was if it was at 100, then it would just be a simple rectangular prism. So yeah, we used 50% and 75% in the study, but that's very customizable to your need. And then this is the north direction. And this is kind of counterintuitive in Grasshopper. I'm not sure why it's this way, but if I switch to a top view, let me plug in the context geometry. These are just CAD mapper files we downloaded from CAD mapper, and we use these as closed breps. So the simpler that you can make these context geometry files, the easier it is on the system, and just makes the process simpler for the script. But if I switch to top view here, so for Minneapolis, north is this direction. I'll draw a little arrow. And so it's 31 degrees off of that y-axis. And for some reason it goes counterclockwise. So we just plug in 31. And now it tells Ladybug which direction is north, which is obviously important because that determines which way the sun is coming from. But if it was 31 degrees in the right direction, then you would have to do 360 or minus 31, which would be like 329 degrees. Yeah, it just goes counterclockwise. I'm not really sure why it's like that, but just keep that in mind. And then, yeah, the context geometry, we have these examples that you can try out just to mess with. But again, these were just taken from CAD Mapper for free. You can just download them and bring them into your Rhino, and it should work fine. And then lastly is the ground level site plan. This is basically the footprint of your building, a rectangle that's kind of representing the largest allowable footprint of your building. Look at that a second. And I'll hide this. So yeah, you can see where it is that our simulation will be run for. And a thing about this surface, that's all it is just a surface that's brought in. But this surface, the dimensions of it need to be perfectly divisible by the grid size. Otherwise, you'll get some remainders and things might not work properly. But if I measure this, it should be divisible by 10 because that's my grid size. So yeah, 320 by 150. So yeah, just keep that in mind. That's another reason why 10 feet is a good grid size. But if you were to use like 12 or something, just make sure that the dimensions of that plane are divisible by it without any remainders. Okay, so I think all of our inputs are set up. We can go over to I have step-by-step instructions here that you can use to follow along. So retrieve the EPW file, we did that. Choose the analysis period. We're just gonna analyze for the entire year. The ground level site plan, we did that. Address the remaining outputs, okay. Turn on the radiation analysis. Okay, so all of the controls that you'll use for like when you're turning stuff on and off and starting the loop, it's all highlighted in blue. So first we need to turn it on. That just turns on the radiation analysis. And you can see that we already get something. Try to find a good view. So you can see what's going on and already how our inputs have sort of affected this. This is our grid size. So each of these grids is 10 by 10. And it's placing a voxel at, so it analyzes the amount of radiation at each of these grid points, and then it ranks them, it sorts them from highest radiation to lowest, and then it places a voxel at the top 50%. So that was that target volume percentage. And this is just for one layer, but when we start the loop, it will go for each layer. Okay, so going back to the instructions, turn on the radiation analysis, and then make sure the output recorder at the end is empty. This is kind of a thing that you have to do when working with anemone. That's what these components are that allow this loop to happen. So we turned it on, but now you just have to empty this by clicking that. So that whenever it starts, whenever we click start, it will run from the bottom up, and it won't have those voxels that it started with at the top. Okay, and now we just double click the loop component, and that should start the process. I'm gonna hide the context geometry just so we can see it a bit better. Okay, and all you do is just double click this, and it moves to the bottom, and it just goes from bottom to top, layer by layer. And once it gets to layer 50, because that's what we specified, and yeah, depending on the size of everything and the grid size, this could take more time or less time. This is a relatively large space that it's optimizing for, and you can see it's going pretty fast. I mean, this will only take a couple of minutes. But yeah, the number of voxel layers in the Z direction is 50, so that's what will tell this to stop at 50. So let's give that a few more seconds. Okay. So I'll turn this off now. And that is our output from step one. And you can see it's very messy. There's a lot of, for whatever reason, there's a lot of noise, like anomalies for, yeah, like on this layer, for whatever reason, this spot received more solar radiation than like spots around it. I don't know what causes these anomalies, but that's what the purpose of step two is. So we'll take this form and bring it into step two, and using cellular automata, which is a type of generative design. And again, I'm not going to go into too much detail here. I'm just teaching you how to use the tool. But this second step is what's going to remove some of this noise from the form and allow this form to be more applicable to our form finding studies. So just plug it into here. And then what I do just to make sure it's like not relying on this component, I just internalize it here. So that like severs the connection, and then I can just, well, I'll just hide this for now. But now this is input into this second step now. So now we're ready to start that. And what this will do you can see it's filled a lot of the holes and tried to remove some of those floating voxels. So effectively smoothing it out a bit. And again, the goal is to make it a bit more usable to us as a form study. And yeah, that's so we're done now. You can see that the step 2 goes a lot faster than step 1. Step 1 just takes longer because of the radiation analysis. But without getting too deep into the second step, this happens via cellular automata. That's what it's called. So it's looking at each individual cell, and it's saying if a cell is empty but it has a certain number of neighboring cells that aren't empty, then it will place a voxel there. It will fill that hole. And then on the other side of it, it's saying if a voxel exists in a cell, but the neighboring cells, a lot of the neighboring cells are empty, then it's going to remove that voxel. So that's basically cellular automata in a nutshell. And these, we reached this set of rules is what they're called, with a lot of like trial and error. So even, if you got a pretty good understanding of this script and this tool, you could kind of mess around with these cellular automata rules and maybe get some different outcomes that way. But yeah, so now we finish with this form, and we can just bake this into Rhino. So I'll do that. And I think the real value of this tool is, even though it's optimizing and sort of solving for just one variable, right? Solar radiation is just a fraction of the things that we have to consider when designing a building. The value of it is that this whole process took less than like 5 minutes, right? The actual simulation, step 1 and 2 combined, it took less than 5 minutes. So like you could just kind of try out a bunch of different analysis periods or voxel granularities, or locations or context geometries. You can just kind of have fun with it, and the actual process itself doesn't take too terribly long. And you can just bake these and make some kind of cool diagrams with them, and that can help inform your form finding studies when designing for solar radiation. And I think that's it. So thank you for watching.